Hi, welcome back. So in this session, I would like to introduce what the stochastic process is, and especially talk about the Markov chain, which is kind of a special case of the stochastic process. All right, so most system changes over time in uncertain manner, and the stochastic process can be used to model some kind of evolution of such a system dynamics. So data plotted on this graphs show the number of the new SARS cases reported each week. And the progress or development of the SARS outbreak may vary from one country to another. But we could observe some similar behavior or the random pattern of initially growing and then hit the top and then gradually the decreasing. So we may model the random pattern or random progress of the SARS epidemic mathematically with the help of so-called the stochastic process. So we're going to talk about what the stochastic process means later on. Anyhow, so it may be possible to answer the following questions. So what is the likelihood of more than 10 cases next week, given that you have reported the cases up to now? Or what is the expected number of weeks that the country will suffer from the epidemic more? So with the mathematical models, we could predict how it will progress over time, and it is also possible to predict the effect of the interventions if we have a certain mathematical model. Let's take a look at the another examples. This graph shows the sequences of the inter-event time of the earthquakes. So what we could observe from this graph is there are some fairly lengthy period, right? Lengthy period with no earthquakes, while there are some other periods with several events in the close successions. So for example, here and here. So we can model the sequences of the inter-event times as a sequence of the random variables. So that is nothing but the stochastic process. So we could answer the following questions with a stochastic process for examples. So does it provide the evidence of some clustering in the earthquake in time? Or there is some clustering? Is the clustering related to the magnitude of the earthquake? So by using the stochastic process, we may answer those questions. All right, so the stochastic process is the process that develops in time according to the probabilistic rules. So the formal definition of the stochastic process is the sequence or collection of the random variables indexed by the set T. So we call T as the time space. And in the set, so element in the set xt refers to the random variable for each time t. So xt can be the number of SARS cases for each t in the first example, and the sequence of the inter-event time xt may represent the inter-event times between tth and t plus 1th earthquake, right? So so these are kind of the examples of the stochastic process. And you may hear about some term stationary. So stationary means it doesn't change over time. So stationary process is the stochastic process in which this probabilistic rules do not change with the time t. Right? And we also need, when you talk about the stochastic process, we need to specify this set of the states or the state space. So state space means the set of the all possible values that random variable xt of the stochastic process can take, right? So some kind of the realization of the xt for each time period, right? So the collection of the possible value that random variable x can take is called the state space. So here are the examples of this stochastic process. So the sequence of the closing prices of the Samsung stock on the tth date in a year, or sequence of number of births in a hospital on day t, sequence of a number of flight arrival at Incheon International Airport during the day t, sequence of a temperature measurement in house at any time t during a day, or sequence of a number of inventory of cars at a dealership at the end of the tth working days. So these are possible example of the stochastic process. We can express those sequences as a sequence of the random variables. And in this slide, I'd like to talk about the several examples of the stochastic process. And the set S, which is the state space, and set T, which is a time space, can be either discrete or continuous. So these two cases, cases are example that the state space is discrete, and these two cases represent the situation that state space is continuous. And these two cases represent the situation that time index, time space, is discrete, while these two cases represent the situation that the time space is continuous. So let's take a look at this case. So both state space and time space are discrete. So the xt, in this case, xt may represent the closing price of the Samsung stock on day t, right? So each day, you only observe the closing price. So you can only observe it in a certain value. Or some number of students waiting for bus at every hour of the day. Right? The sequence of xt such that xt represents the number of students waiting for the bus at every hour of the day. So every hour, so discrete, right? So every hour. And then you observe certain number of students. So number of students can be expressed as a discrete number. So 1, 2, 3, and so on. Right? So that is the example of the situation that the both S and T are discrete. So here's the cases that the S is the discrete and T is continuous. So xt is the price of the Samsung stock at the time t on a given day. So the stock prices change over time and then remain here and then change to here, 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 and so on. So here is the kind of example of the case. And the xt, number of students waiting for bus at any time of t. So you keep measuring the number of students over time. So you're continuously monitoring the number of students. So number of students itself is a discrete, but you measure the number of students over time. So that is the time space is continuous. So over the time, you measure the number of students, right? So state space is discrete while the time space is continuous. So you can take a look at the other cases easily. So for example, in the last cases, both S and T are the continuous. And the example can be xt represent the temperature at the airport at the time t. So you monitor the temperatures. So the temperature is kind of the continuous in the values, right? So you continuously monitoring the temperature over time. So in that case, both S and T are continuous. Right. So why we try to use the stochastic process to model the evolution of the dynamical system? Well, so if you can represent the evolution of the dynamical system by using the sequence of random variables, So we can, answer the following questions. So for example, you may, by using the sequence of the random variable, you may calculate the conditional probability. In other words, given this history, and then you are currently at the kth stage, so what is the probability that xk plus 1 is equal to a certain value? So by using this stochastic model, you can predict the future based on the history. So that is it can be used as a means for forecasting, right? Or if you can calculate this condition probability, you can calculate this condition probability as well. That means, so initial state is 7. What's the probability that the state of the system will be 10 after 2 time period? Well, by using this condition probability, you can answer those questions. So if you can calculate this condition probability, you can also calculate the expectation as well, right? Also, by doing so, you may calculate some kind of long-run average, or you may answer those types of examples. For example, what is the probability that within a given hour, all circuits of some telephone system become simultaneously busy? Right? So if you can possibly model the evolution of the system, a dynamical system, as a sequence of random variable or stochastic process, you can answer those types of the questions. Right, so we're going to take a look at the definition of the discrete time stochastic process. By taking a look at the term discrete time, you can easily see that discrete time stochastic process is a stochastic process when the time space is discrete, right? So x0, x1, x2, and so on. So you can do it. So we here consider the discrete time stochastic process having the discrete state space as well. So we basically assume that we are interested in a stochastic process where both state space and time space are discrete. Right, so let's take a look at the basic important concept called the Markov property. So Markov property simply says, if you know the present, future is independent of the past. Formally, what does that mean is, given the history, right, the past and the present, if you know this, the conditional probability of the future, given that you know the present and the past, is equal to same as the probability of the future given the present. So that the future is independent the past, given that you know the present. That is called the Markov property. Sometimes it is called the memoryless properties. So why we talk about the Markov properties? The stochastic process having the Markov property is one of the simplest stochastic process model. The simplest model is, so this is the stochastic process, right? One of the simplest cases is the situation that xt is IID, identical and independent cases. So in that cases, xt is independent to each other. So conditional probability is same as the probability of the itself, right? And xt is identical over time. So you just simply take a look at the single random variable, and that's it. So there is no more calculation about this kind of conditional probability. if you think about the conditional probability, the most simplest cases must be the stochastic process having this Markov property, right? As already mentioned that by using the stochastic process, we may interested in the forecasting, the prediction on the future given the past. If the Markov property holds, this conditional probability is equal to this, right? The future is independent of the past given the present. So basically, we try to take a look at the stochastic process having the Markov property first because it is one of the simplest cases in terms of the stochastic process. So that is one of the simplest thing to analyze. Right. So the stochastic process having the Markov property is called the Markovian process. So we are interested in discrete time Markov chain. Discrete time Markov chain is a stochastic process, right? With the state space S. So the state space is a discrete. So Xn belong to this state space, right? So Xn, which is random variable, takes the one value in the state space. And for Oi and J in the state space, this conditional probability, this is the past, this is the present, and this is the future, right? So past, present, and future. This conditional probability is equal to this. The future only depends on the present. Well, so that is called the one-step transition probability. That specifies what is the probability that we're going to have we're going to have the J, given that we are currently in the system is currently in the state I, right? So that is called the discrete time Markov chain. That is the one of the stochastic process. Right, so we especially interested in time homogeneous discrete time Markov chain. What does the time homogeneous means? Time homogeneous discrete time Markov chain is the discrete time Markov chain having the stationary transition probability. That means this conditional probability is independent of the n. So for example, this conditional probability, when n is equal to 0, is equal to this conditional probability when n is equal to 399. And that is equal to this conditional probability for every n. Right? So that is the assuming of the time homogeneous means the law of the evolution of the system is time independent. So when we talk about this conditional probability, we don't need to consider the n, right? So I can simply represent the Pij to represent this conditional probability, right? So we note that the Pij, if you sum of the Pij over all j is equal to 1 for every I, right? So Pij can be specified in the form of the matrix. That is called the one-step transition probability matrix. So when we build up the matrix, you just list all possible state that xt can take, and in the column corresponds to all the state that xt plus 1 can take, right? So I throw in j's column represent this one-step transition probability from state I to state j. All right? All right, so we're going to take a look at the examples for better understanding of the Markov chain. Right? So in this example, a mouse starts from the cell 1 in main J. maze in this maze, right? And this mouse is in absence of the learning or memorizations. So when the mouse choose the next cell and it chooses the next cell equally likely among the adjoining cells. So for example, from this cell, there are two options to choose, right? Either going down or moving to the right. And the mouse choose, equally likely among these two options. So we can say the probability to choose going down is equal to 0.5 and equal to 0.5 and so on, right? So suppose that mouse is in here and the mouse choose the 4 directions equally likely with a probability of 0.25. So that is something how the mouse choose the next cell to move. All right, so assume that once mouse finds either pieces of cheese or cat, it will understandably stay there forever, right? There is no more changes from that cell. So let's say xn, right? xn represents the position of the mouse after n changes of the cell. So we try to model the sequence of random variable, and each random variable represents the position of the mouse after n transition. Okay? The question is this Markov chain? Is this Markov chain? So in order to understand whether that is the Markov chain or not, you first to specify the possible. You need to specify the state space first, and then see by using the state space whether you can express this Markov chain by using the one-step transition probability transition matrix, right? So state space in this case can be, because this xn takes the position of the mouse, right? So we have the 9 possible positions, 1, 2, up to 9, right? The state space consists of the element 1 through 9, right? So the next question is this Markov chain? So in other words, can we express this situation by using the one-step transition probability matrix? Okay? So probably let's construct the one-step transition matrix. So I list all possible state 1, 2, 3, 4, 5, 6, 7, 8, 9. And this is the case xn, right? And then xn plus 1, which is next state. 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, so suppose that mouse is in the current cell 1. He can choose either 2 or 4 equally likely. So that means equally likely 1/2 and 1/2. And it is not possible to choose the node cell 1, 3, 5, 6, 7, 8, 9. If you think about node 2, suppose that mouse is in the cell 2 and he can choose either this way, or this way. So next node to visit could be, next cell to visit could be cell 1 and cell 2, cell 5 and cell 3. And the mouse choose equally likely. So that means the probability to choose the cell 1 is 1/3, 0, 1/3, 0, 1/3, 0, 0, 0, 0. Suppose that mouse is in the cell 3 based on the assumptions, the mouse stay in the cell forever. So mouse is currently in the cell 3, and he will remain in the cell 3 forever, right? So that is the like this, and so on, right? And if you think about the 5, suppose that mouse is in the cell 5, and he could choose the next cell, either 2, 4, 6, and 8. And mouse chooses, among these 4 cells, 4 possible cells equally likely. So 2, 1 over 2, 1 over 4, right? And the 4, 1 over 4, the 5, and 6, 1 over 4, and the 8, 1 over 4, and 0, right? So you can do for cell this row, this row, this row, and this row, and this row. So you can do by yourself. So I think we can successfully construct this one-step transition matrix, right? So that means probably I would say that this stochastic process, which is the sequence of the position of the mouse after n transition, is indeed a Markov chain with this one-step transition probability matrix. Okay, so in the session, we talk about the stochastic process. Stochastic process is the collection or sequence of the random variables. And we also talk about the Markov properties. So given the present, future does not depend on the past. That is the meaning of the Markov properties. And we take a look at the stochastic process having the Markov property. So that is, especially, we take a look at the discrete time Markov chain. And discrete time Markov chain with the discrete state space can be characterized by the one-step transition probability, especially time homogeneous discrete time Markov chain cases. All right, so that's it for today. Thank you.